Stars are what precede all the existence of life as we know it, not only in the sense of the sun warming the earth to make life possible, or the constellations guiding humanity to an advanced civilization, but forging all the elements that make up the universe, acting as a furnace. What are the stars? Where do they come from? And what is their fate? My name is Jack.
And I'm Eddie.
And we'll be covering the life of a star.
First, let's understand what a star is. We can imagine them as large nuclear reactors. Stars consistently radiate energy, and that energy needs to be fueled by something. In this case, it is the process of nuclear fusion. This process is a nuclear reaction in which atomic nuclei of low atomic number fuse to form a heavier nucleus with the release of energy. Nuclear fusion in the sun is not a one-step process, with two hydrogen atoms coming together to form a helium atom. This process can be broken down into steps that explain how solar radiation is formed. First, two protons collide because of extreme conditions in the sun's core. Most of the time, the protons don't bond and just go their separate ways. But sometimes, one of the protons becomes a neutron, thus forming an atomic nucleus with the other portion of releasing a proton and neutron. The name of this atomic nucleus is deuterium. When a third proton collides with deuterium, helium-3 is formed, and gamma radiation is released. This radiation comes out of the sun's core and is released as sunlight. Finally, another helium-3 collides with our initial helium-3, forming helium-4 and releasing two protons. This proton, sooner or later, will also collide with other protons and make nuclear fusion, thus generating a chain reaction.
The mass of helium-4 formed as the final product is less than the mass of the four hydrogen atoms used in the process. This occurs because a part of the mass has been converted to energy and released by the star in the form of light and heat. This is where the energy generated by the nuclear fusion comes from, which prevents the star from collapsing. The relationship between the energy generated and the mass used can be obtained by the equation E equals mc squared. E represents energy generated, M represents the mass converted during the process, and last, C is the constant speed of light, which is squared. Nuclear fusion is important for the star not to collapse. This is because the mass of the star is so large, gravity will always try to compress the star to its smallest possible form, and this intensifies the greater mass of the star. At this point, the energy released by the nuclear fusion takes place in the core of the sun and forces it to layer against gravity, thus not letting gravity win, but also not making the star explode. This establishes a balance called hydrostatic equilibrium, meaning the condition of a fluid or a plastic solid at rest occurs when external forces such as gravity are balanced by a pressure gradient force.
The life cycle. First, a fundamental characteristic that determines the life of a star is its initial mass. A star's life cycle, from birth to death and all the stages in between, will span millions or even billions of years. It begins with a nebula, a cloud of gas and dust in space. Gravity causes the nebula to collapse inward, and as it does so, it begins to spin. This causes the center of the nebula to become hotter and denser, forming a protostar. The protostar continues to contract and heat up until it reaches a temperature of about 15 million degrees Celsius, which is hot enough to ignite nuclear fusion in its core. At this point, the protostar becomes a true star and enters the main sequence phase. In the main sequence phase, the star fuses hydrogen atoms together in its core to form helium, releasing energy in this process. This energy is what makes the star shine and provides the necessary pressure to keep the star from collapsing under its own gravity. The length of this phase depends on the mass of the star. Low-mass stars, like our Sun, can remain in the main sequence phase for billions of years, while high-mass stars can go through this phase relatively quickly. When a star exhausts the hydrogen in its core, it begins to fuse helium into heavier elements, such as carbon and oxygen. This causes the core to shrink and heat up, while the outer layers of the star expand and cool. the star becomes a red giant, a massive and luminous star with a diameter that can be many times larger than the sun. This phase can last anywhere from a few 100 million to a few billion years.
Eventually, the star's outer layers are blown away, leaving behind a hot, dense core called a white dwarf. A white dwarf is no longer producing energy through fusion, but it still radiates heat and light. Over time, it cools away and fades away, becoming a black dwarf. However, stars that are much more massive than our sun can continue to fuse heavier elements and eventually reach a point where the pressure created by the fusion can no longer counteract the force of gravity. This results in a supernova explosion, which can outshine an entire galaxy for a brief time. The remnants of the explosion can form a neutron star, an extremely dense and highly magnetic object made of neutrons, or a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape.
How we know? Our understanding of the life cycle of stars has been acquired through a variety of sources, including the observation of visible light, radio waves, X-rays, and other forms of electromagnetic radiation. Scientists use telescopes and other tools to gather data and interpret it to grasp the physical characteristics of stars and how they develop over time. Spectroscopy, which is the study of the light that is released or absorbed by a star to determine its chemical composition. Temperature and other properties is one of the most crucial tools for investigating stars. By examining the spectral lines, which are a spectrum in which light of only a certain wavelength is emitted or absorbed, rather than a continuous range of wavelengths or a continuous range of colors created by a star, scientists can determine the elements that exist in its atmosphere and deduce its temperature, density, and other traits.
In recent years, advancements in technology have allowed scientists to study stars in even greater detail, such as with space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory. These instruments have enabled scientists to gain new knowledge about the structure, composition, and behavior of stars, and improve our understanding of how they form, change, and ultimately die.
Ethical issues. The study of stars often involves the use of advanced telescopes and other technologies that require significant financial resources. As such, there can be ethical concerns about allocating resources to the study of stars when there are pressing social issues such as poverty, inequality, and access to healthcare that require attention and resources. Furthermore, some people may view the study of stars as a luxury or indulgence rather than a priority for scientific research.
Cultural issues. Different cultures have different beliefs and mythologies related to stars, which can create cultural tensions and misunderstandings. For example, some indigenous cultures believe that stars are the home of their ancestors, and therefore they consider them sacred. Western scientific methods of studying stars may conflict with these beliefs, and there may be tension between the scientific community and the indigenous communities. Environmental issues. The life of stars can have significant environmental impacts, particularly when they reach the end of their life cycle. For example, when a star explodes in a supernova, it can release a large amount of energy and radiation that can have harmful effects on surrounding planets and celestial bodies. Additionally, when a star collapses into a black hole, it can generate powerful gravitational forces that can disrupt nearby celestial bodies. Thank you for listening.